Okay, folks, I am going to go ahead and get started. The first thing I just wanted to mention was the exam on Thursday of last week. I know that when I talked to everybody in lab, goal was to get you the exam back by Thursday of this week. However, I forgot I'm not going to be here Thursday. Dr. DeRocher will be taking class for me, and 2 other people will be taking lab. That, and between it and having, so I don't usually try to talk about medical issues. I've got fibromyalgia real bad, and I had an attack that lasted 4 days, and so I'm still recovering from it. And basically it means that I can't grip anything or write or do anything. So I haven't gotten started on grading because I couldn't hold a pencil or a pen, whatever. So I will have the exams back to you on Tuesday of next week. I apologize. Normally they're going to be back the week after. It's just, it wasn't a physical possibility. It's literally a physical possibility this particular time. So I will have your exams to you on Tuesday. Before I move on to the rest of the week, anybody have a question about the exam? Was it straightforward relative to what we had discussed? Did I throw you a curveball that you weren't expecting? If so, let me know, because I try not to throw curveballs. If you do my optional homework, most likely there's no curveballs. So I wonder how many people did the optional homework, because the test, most of the questions on the test look just like the optional homework. And the only curveball may have been I used apothecary units instead of regular units. But all you had to do, I gave you the apothecary sitting on the back, so it was literally still a dimensional analysis. I wondered, did you know the process of dimensional analysis? So that's why it was a little bit different. But hopefully, relatively speaking, there were no major shocking problems on the exam, which is all I'll ever guarantee for you. So now you have an idea of how to study for my class. The optional homework is an exceptional way to study. And that way, and I'm not one to throw a lot of different, I don't try to throw curveballs. Chemistry for a lot of people is a curveball, and I don't need to add to it. So, okay, the next thing I wanted to discuss is Blackboard. So I had started doing something first thing this morning, and at 7:45 I got information about lab, and so ignore what's on the Blackboard at the moment. It's about to change. All that I got up was that first page, because again, I couldn't even, when you got fibromyalgia, it hurts to touch anything. So I literally tossed and turned in bed all, and took medicine to make me sleep so that I wouldn't feel it. But anyhow, so I'm just now getting everything typed up. I will get it finished. You will have all the information by, hopefully by 10 o'clock this morning. So it shouldn't take me too long to finish. It just needs to be done. So on Thursday, you will have Dr. DeRocher for class. Dr. DeRocher, if you have any complaints about me, that's a good time. No, hopefully not. But Dr. DeRocher is my chair, and he would be the one to address anything if you have comments. Hopefully you won't talk too bad. That's always a nerve-wracking thing for me. I hate evaluations for the same reason. It's just nerve-wracking. I take them so seriously that I'll make myself sick when I see they're coming in until I get done. So, but anyhow, Dr. DeRocher will be here on Tuesday morning. He'll be discussing atom size, ion size, and trends associated with the element, with the atoms of the elements and their ions. And then those that have the 1050 lab will have Dr. Barber. He will be in there as me. He'll be in lab as me. You'll still have your TA in there. And you'll be doing the separations lab, which basically is separating sand and salt. It's not a hard lab. It's time consuming because you got to be patient, but it's not hard. And then Dr. Wei Yang will be in the afternoon lab. So that will be Thursday. Any questions about Blackboard or Thursday? Because I am not here on the quiz on Tuesday next week, I won't ask Thursday questions until you have a chance to ask me questions. So I'll make it just over the material today, and then the following quiz will be over the stuff that would have been this Thursday and next week. That way, because I know throwing students into different teaching styles sometimes can be a problem. Which brings up the teaching style. Dr. Duration will not be getting on Zoom. So if you're on Zoom, don't plan it for Thursday. If you're not, don't plan it for Thursday, because Dr. Duration will be in person and he will not be doing Zoom. Any questions? Okay, the last thing I wanted to mention, I try to keep up with all of the options of bonus points. Some of you may have an email about career preparation stuff, a career preparation thing that's a bonus point opportunity. Another one that's a 5 bonus point opportunity is happening this Wednesday, and I just found out about it today, so I haven't been able to advertise it. It will show up under your bonus folder today, but it's called the Science of Politics. Basically once a month, the last Wednesday of every month, we have a Science Wednesday, and I always use those as bonus opportunities. The Science of Politics, there are 2 options for attending. The first option is going to be, is the only one I have written here. It's going to be an LSC 102. The other one is a Zoom option. And again, you're going to have to look at the flyer that I'll post to get the Zoom link. And that will be from 6:30 to 7:30 p.m. Now, if you are there in person, I have a feeling that Dr. Ashley Hicks, who is in charge of it, will probably have a way for you to sign in. Make sure you do so, or have her sign something. If she doesn't have a sign-in sheet, have her sign something to let me know you attended. If you're on Zoom and she does not have, I would go ahead and take a picture of the Zoom, so that the Zoom screen, just in case, but normally she'll tell me who attended. And even on Zoom, it's expected that you attend the entire time and that you are there, because when they are done, if she has to turn you off and you're still online, she's going to assume that you ghosted. So you actually have to be present, which I enjoyed having so many people at that conversations with chemist with the crime lab. I hope those that came enjoyed the talk. It was kind of interesting to hear all the options with the crime lab, and there will be more options for you to get involved. But any questions about that? Again, this is a 5-point bonus opportunity, and it's strictly for attending. There's no quiz or anything on it.
That's tomorrow.
That is tomorrow. Yes, it is tomorrow. Sorry, I did not put the date. So what is today? 9/27, so 9/28. Yes. Lewis Science Center. Other questions for me? Okay, sorry about all of the announcements. Hopefully I've covered everything. And yes, I will have a homework posted today, and I will have a homework posted over what Dr. DeRocher is going to go over. I will probably extend it so that it is also due on Wednesday, along with the next homework, so that you have time to ask me some questions. Because I really do worry when you change everything up, that something gets lost in translation. So I want to make sure you have a chance to ask me questions. So I'll make sure that that's not due until the following Wednesday. instead of the Tuesday or the Monday that I normally have it due. Okay. So let's get into today's information then. Prior to the exam, we started talking about electron configurations, and there were 3 types of electron configurations we dealt with. We dealt with the basic electron configuration. We dealt with the noble gas electron configuration. And we dealt with the box diagram. I want to start with about 3 more elements of discussion. And then we will move into talking about anomalies. And then we'll move into talking about ion formation and electron configurations. So if I recall, on Tuesday of last week, we talked about hydrogen, helium. I think I got lithium in there, and then I jumped to carbon. And as I did lithium and carbon in particular, you had a handout you could look at, and you could fill in how the electrons filled into the atom, and that was to give you an idea of what everything looked like. What I want to do first, before we get into some of the other information, is I want to go further down the periodic table, because I want to get into the transition metals and things of that nature. So before I do that, as a reminder, roughly, keep in mind my drawing is always a little bit off. As a reminder, this section would be the NS, whoops, I always do that. NS section, where N is equal to X and X is equal to the period number. The right-hand section, oh, and that does include helium. Before I go further, that does include helium. The right-hand section is the NPs. Where again, N is equal to the period number. In the middle, you have your transition metals. Your transition metals are the ND, but in this case, N is equal to X minus 1, so that the period number is always 1 higher than the principal quantum number. And then when you think about your F series or your F grouping, this grouping is known as the NFs, where in this case, N is equal to X minus 2. So it's always 2 less than the period number for those intertransition metals. So that is, I mean, folks, I also think I gave you a periodic table that actually listed them out. So it's up to you how you memorize things. The nice thing about the periodic table is you don't have to worry about memorizing the order of energy, because it's already outlined for you. Okay, so let's look at some examples. Let's skip down to sulfur. Sulfur is element number 16 on the periodic table, so it has 16 protons and 16 electrons. When you fill in electron configuration, you always start at the top of the periodic table. So we're going to start with period 1 and the S block. The maximum number of electrons that can go into any S subshell is 2 because S only has 1 orbital available to it according to quantum numbers. That takes care through the first row. So now we're to the second row. In the second period, the first thing you encounter is the S block. And again, the maximum number of electrons in an S subshell is 2 because there is only 1 orbital in an S subshell, as indicated by the M sub L value. Then you move over to the right-hand side, which is the P block. And we're in the 2Ps. The maximum number of electrons that can fit into a P is 6. Because when you have an L of 1, which is a P subshell, that means you have 3 M sub L values or 3 orbitals. Each orbital can only have 2 electrons, so that's a total of 6 electrons. We move on down to period 3. And the first thing you see in period 3 is the S block. And again, S block, S orbital, S subshell. S subshell has only 1 M sub L value. So in other words, it has only 1 orbital. Therefore, the maximum number of electrons is 2. And then we move over to the P block. We're in period 3, P block. And sulfur is the 4th element in that period. And if you add up the superscripts, it will equal 16. Questions? Trying to remind you of some things. Now to get to the noble gas configuration. If you get to the noble gas configuration, you find the noble gas that was right before sulfur. So the noble gas before sulfur is that of neon. By placing the elemental symbol for neon in brackets, it means that I can ignore the electron configurations from period 1, and I can ignore the electron configurations for period 2. I only need the electron configuration for what came after neon, which is the period 3 portion. So that would be the 3s2, 3p4. To write the box diagram for this, we'll write it the long way. Again, the difference between the box diagram and the complete is simply, we are now going to break things down into their orbitals. So I kept saying that if you have for instance, if you have an S orbital, that means L is equal to 0. I'm sorry, if you have an S subshell, that means L is equal to 0. If you use the calculation, that means that the only acceptable M sub L is the 0. So there's only one orbital. And so it's just 1 line. And there are 2 electrons. That is going to be true for every S. The maximum number of orbitals in an S is 1. For the P, that means the subshell is equal to 1. That means L is equal to 1. And if L is equal to 1, that means M sub L can be a -1, a 0, or a 1. In other words, there are 3 orbitals for the P subshell. So we draw 3 lines. And in this particular case, all of the lines are full because there are 6 electrons. Moving to the 3s, again, S orbitals will only have 1. There will only be 1 orbital for an S subshell. And then we move to the P. Again, with the P, you're going to have 3 orbitals. Now, these are degenerate orbitals, meaning when we say the word degenerate orbitals, what we mean is that there's more than 1 orbital per subshell. That's all. So anything other than S is going to be a degenerate orbital. And when you have a degenerate orbital, you place one electron in each orbital spin up before pairing. Now, just as a reminder of quantum numbers, let's just do the ones in the P here, in the 3P, not all of them. So just as a reminder of how to get to quantum numbers, the numerical value is going to equal your principal quantum number n. The letter is going to tell you what L is. The arrows are going to tell you what M sub S is. And then we will assign our M sub L. And the way you get to M sub L again is you remember that. So if L is 1, if L is equal to 1, which it would be for a P subshell, then it can be any number between -1 to a +1. So it can be a -1, 0, or 1, and we literally will assign our lines accordingly. So we're going to assign this as -1, 0, 1. When we write our quantum numbers, we're going to do so in the format N, L, M sub L, M sub S. In other words, we're writing them in order of from biggest to smallest. How far away from the nucleus? In what type subshell? At what, on what axis? And then is it spin up or spin down? So you're getting very, very detailed as you go. So it would be, for the first electron that we put in, it would be a 3, 1, -1, 1/2. That was the first electron we added. Our second electron would be a 3, 1, 0, 1/2. Our third electron would be a 3, 1, 1, 1/2. And our fourth electron would have been a 3, 1, -1, -1/2. Questions? Again, this is more trying to remind you of what we were going over a week ago. That's a long time to hold all this in memory, I think. Questions? Okay. Let's go to another one. Let's look at vanadium. Element number 23, so 23 protons and 23 electrons. Again, you start at the top and work your way down. 1 S with 2 electrons, that takes care of period 1. Period 2, the first thing we come across is the S, and there are 2 groups in S, so 2s2. Then we move over to element number 5, basically boron, which starts the 2p, and we go through that entire grouping, so that's 6. Then we move to period 3, and we go through the S block, 2. There's 2 electrons in an S. Then we go to the P block, where we'll get 6 more electrons. Now this is where it gets interesting again. As soon as you open up the third shell, as soon as you get N is equal to 3, the principal quantum number 3. The S, the P, and the D become available, but they don't necessarily fill in that order. That is why the periodic table goes from 3P to 4S, is because technically the fourth principal quantum number, the S subshell, is slightly lower in energy than the D. Again, S can only fit 2, and then we go back to the 3D, where you'll get 3 of them. So again, as soon as I opened up the third shell, N is equal to 3, all of the subshells came crashing in, the S, the P, and the D. But that does not mean they are filled. So we filled the 3S, we filled the 3P, but then we had to fill the 4S because it's slightly lower in energy before we came back to the 3D. Now, I'll admit, once you get past, say, calcium, I tend to go straight to the noble gas. So, but I still want to write out the full ones at this point. But if we were to write out the noble gas, it makes life a lot easier because it's going to be argon, which takes care of everything through period 3. So we only need to include what's in period 4 on, which is the 4s2, 3d3. Now, I'll admit also, once I get to this, let's face it, it's the outer electrons, as we're going to talk about when making ions, that's super important. So I tend to use the noble gas configuration and go, okay, this is going to be argon 4s. S subshell has only one orbital with 2 electrons. And then I get into the D. The D subshell, in the case of a D subshell, that means L is equal to 2. So it's a D, which means if we're looking at a number line, M sub L is everything from a negative L to a plus L. So it can be everything from a -2 to a +2. So we have 5 orbitals in the D subshell. So we're going to draw 5 lines. Now, because there is more than one orbital in this particular subshell, it is a degenerate orbital, which means you're going to put one electron in each orbital before pairing. So we're going to put in the 1 electron in the first 3 orbitals of 3D. Questions? Now, folks, this same process can happen, and I'm not going to go through step by step, or I'm not going to say everything, but let's say I were to give you lead. Lead is element number 82. So it's going to have 82 protons and 82 electrons. Once you get basically anything in the later periods, you'll see why it's so important to use the noble gas configuration. But following the same things I've been doing, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We go through all the way through the 3d10. Then we pick up the 4p6, 5s2, 4d10, 5p6, 6s2, and this is where I have to start being careful. Who can tell me why I got to be careful at this point once I get past 6s2? Because I have to pay attention to the Fs. Right now at 6s2, I'm at barium. You will notice that once I get to lanthanum right past barium, I have a jump. that I would have to take into account. Now, unless I'm working with a inner transition metal, a lanthanide or an actinide, I won't write 4F1 yet. I will wait and combine them all so that they're all in one statement. So in this particular case, I would wind up, I'm not 4F1, 5D1. In this particular case, I would write the 4F14, and then I would write 5D10 and 6S2. So again, the big thing here is you did have to pay attention to the fact that the lanthanides jump down. I mean, after lanthanum, it jumps down to the lanthanide series, the inner transition metal. Huh? I meant not 6S, I meant 6P. Thank you. 6P2. It's hard to talk and write some days. Questions about that? Now, folks, obviously this is where the noble gas configuration comes in, because by saying xenon, I don't have to write anything. I don't have to include anything before this point. I only had to include what came after xenon, which was the 6S2, 4F14, 5D10, and 6P2. Much better. Much less chance of screwing it up. Yes. It's always the noble gas that came right before the element. So literally, I took lead, which was 82, and I backtracked to the noble gas report. So basically, by doing so, I take lead, backtrack to the noble gas that came before it, that's xenon. So I can wipe out everything above it, above the row that xenon's in. So I only have to start here, because that's the number literally after xenon.
So then you use the like section.
Or this is the NX, or the NS, where N is equal to the period number, so 6S. This is the N minus 1, I mean, X minus 1D, well, ND, which is X minus 1. So since X is 6, that means these are the 6 minus 1, or the 5Ds. But I did have to pay attention that this went down here at some point. So I could have written the 5D and then the 4F, or the 4F and then the 5D, just to keep them all together. That part didn't matter at this point. The only time it would have mattered is if I would have stopped here and say I went to gadolinium, then I would have had to have written the 5D1, 4F, 7. Because technically that one element did come out of the Ds. Otherwise, if you're going straight through it, you just cram them all together, and it doesn't matter the order. Other questions? Did that answer your question? Okay. Other questions? Okay. Now, folks, before I move on to, well, the next thing I want to talk about are the anomalies. What is an anomaly first? What's the definition of an anomaly? Something out of the ordinary. In this particular case, what we're referring to as ordinary is writing electron configurations the exact way we just read them. That's ordinary. But throughout the periodic table, there are elements that do not behave in the ordinary manner. Now, I'm not going to make you memorize all of them because, to be quite honest, there would be several and it would be hard to keep up. But there are two groups that I am going to make you know as an anomaly. Those two groups are group 6 and group 11. Group 6 and group 11 contain elements that are anomalies. All of them. And they all behave the same way. So I'm not going to make you memorize a bunch of different ways. I'm going to make you memorize one way for each. Now, whether it's in group 6 or group 11, what happens is you promote one electron from the S subshell to the D subshell. Now you may ask, why do the atoms do this? Why do the atoms in group 6 and 11 behave this way? Well, first thing you have to realize is that technically the S and D subshells are very close in energy. I gave you a drawing when we started this discussion, and I showed you that the only reason D filled first or the S filled first is because of this little bitty fraction of time, this little bitty fraction of electron density that came before the D. But in reality, they're so close in energy. Now, the promotion. Leads to a more stable electron configuration. Because 2 half-filled or 1 half-filled, 1 full subshell is more stable than partially filled shells. So for example, let's look at chromium real quick. Chromium. If we were to fill it normally, so the normal way, it would be argon 4s2 3d4. And if we were to look at these last pieces, whoops, it would look like this. This is a full shell, but this is considered a partial because it's not half or it's not full. It's so if it's not half filled or if it's not full, it's considered a partial. Now, chromium, which is in group 6, will promote this electron to the 4s. So the reason it is an anomaly is because if we do that, we get argon 4s1, 3d5. So that is going to be 4s, 3d. And you will notice that that one electron that we promoted winds up with giving us a half filled and a half filled, which adds stability to chromium. So partial is, there's only 3 possible definitions. It's either half filled, full, or it's considered to be a partial. And anytime you can get 2 half filled or a half filled full, that's better than a filled partial. So another example would be that of copper. If I fill it normally, it would be argon 4s2 3d9. And again, what you have here is you've got a full and what is considered to be a partial. But by allowing that one electron to be promoted, the electron configuration that you get for the anomaly is argon 4s2 3d10. I'm at 4s1, excuse me. I automatically go to 2. It's habit 2. I have to go back and look at what I'm doing. 4s1 3d10. So what you wind up having is you wind up having a half and a full, which again adds stability. Folks, I'm not asking you to memorize all of the anomalies on the periodic table. I'm asking you to know group 6 and group 11. My typical suggestion when you get to a test is to put a star by group 6 and group 11. That way you remember, oh, I need to treat that one as an anomaly. But again, they're anomalies because of the fact that we can create something that is stronger by promoting only one electron when we're talking about the energy levels being very close to one another to begin with. Okay, at this point, before we go to the ions, what I want to do is I want to talk about what the orbitals look like. I mean, we already know that an S is a sphere. And a P is a dumbbell. And a D is a clover leaf, or there is one of them that is a dumbbell with a donut. And then I can't draw the F's. But what do they actually look like when we start stacking things on top of each other? If you look back here somewhere, oh, this one's good. I stacked on top of the two P's, I stacked a 3P and a 4P and a 5P. On top of the D's, I stacked a 3D, a 4D, a 5D. Oh, I actually stacked a 6P too. So what does it look like when we start stacking all these orbitals on top of each other? And how do I know? Before I get into showing you what they look like, I want to talk about some basics. So we have the S subshell. We have the P subshell, the D subshell, technically the F subshell. When does the S subshell first appear? What N value? What principal quantum number value is the first time we find an S? N is equal to 1. That's the first time we find an S subshell. What principal quantum number is the first time we encounter a P subshell? What is the first time we encounter a D? And a 4 for F. You're going to need that information for understanding what orbital you're looking at. This will help you to this and the shapes help you identify what orbital or orbitals you are seeing. If you don't know that information, the next part would be tough. The next thing, before I get into it, is I want to talk about nodes. I briefly mentioned nodes the other day. A node is an area where electrons do not exist. The total number of nodes is going to equal n minus 1. The next thing you need to know is that there are radial nodes and there are angular nodes. What word does radial have in common? Radius. So in other words, we're looking around for a circle. So that could be present. The radial nodes will be n minus 1 minus L. And the angular nodes will be total minus the radial. So to see this in action, we're going to go to a file. Oh, I've got a key already. That's my key. Don't want the key. There. This is actually your homework. It's the homework for this, but I'm hoping to explain it using these diagrams. So, okay. The first thing I ask myself when I look at this first one is, what does it look like? An S, a P, a D, or an F? S. Ugh. So we have an S. I hate when I do that. Let's try this again. We have an S. Now, what is the first N? What is the first principal quantum number that an S can be found in? 1. So it starts at N is equal to 1. So this is the 1s. That must mean this is the 2s. So we're talking about the 2s orbital here. Now the total nodes, which I have the definition right here, total nodes is equal to n minus 1. So in this case, it would be the total nodes equals n minus 1, which is equal to 2 minus 1, or in other words, there is 1 total node. Now, the radial nodes is n minus 1 minus L. So this is equal to n minus 1 minus L. So it's 2 minus 1 minus the L value. So what is the L for an S subshell? 0. So that would be 1. And it is right here. That would be the area where that radial node exists. So this is, the angular nodes is total minus radial, or 1 minus 1, which is equal to 0. That one wasn't so bad, right? That is mostly obvious. Let's get into the next one. This one's a little harder to see, but let's start. What is this type of orbital? It's a D. Where did the D's begin? In the third. So here's where it gets tricky. This little bitty inside one that you can barely see is the 3D. Then you have one that is a touch larger. That would be our 4D. Then you have one that is even larger. Which would be the 5D. So this is the 5D. Let's see if I can blow up the picture so you can see it better. Well, it doesn't want to stay blown up. That's the problem. It doesn't want to stay blown up, so hopefully me blowing it up temporarily helps you see it. Okay, so the total nodes is equal to n minus 1. Well, n is equal to 5, so 5 minus 1 is equal to 4. So there are 4 nodes in this 5D orbital. Now your radial nodes is equal to n minus 1 minus L. So that is 5 minus 1. And what is L equal to when you have a D? 2. So minus 2. That means that that is equal to 2. And then the other is the total minus the radial. So that's going to be 4 minus 2, which is equal to 2. So now let me show you where they're at. Help me do that. I'm going to erase, if it'll let me. There we go. That piece. So, and I need a color that's going to show up well. Let's start with this black. So for the radial node, I'm going to draw it and then I'll blow it up so you can see it. There are 2 radial nodes. Keep in mind, I am talking about radius here. Zoom out. Delete. Let's see, there's the other one. So on that, you have 2 radial nodes. You have one between the 3D and the 4D, and you have one between the 4D and the 5D. Because they form a circle. Now the angular nodes are going to be the ones that go with the XYZ coordinate plane. So one is on one of the axis and the other one's on the other axis through the middle of this thing. Those are your radial nodes. I'm sorry, those are your angular nodes. The radial nodes are circles, the angular nodes are axes. Does that help you picture what to do with these orbitals? So like this next one I see is a P. Where do the P's begin? N equals 2. So I have a 2p and I have a 3p. So this is the 3p. So that's how you have to do these types of things. Now, I'm not expecting you to draw the radial or angular nodes other than just knowing what they are and how to determine how many of each. Any questions? Hopefully that helps some. You can do that. Now, I'm not going to try to do that with F because F gets complicated fast. I do want to show you what one will look like if I can find it real quick on Chem 101, because it looks a little bit different than these do, but still similar. So let's see, work apps, active. Okay, good. Let's go in. No. Practice. No, I don't care about that. I don't know. Oh, I forgot about that. But he has to go. Okay, let's see if it's in here. Okay, so if I were to give you this, it's telling you the node is in white. So what is it? It's the 2s. If I were to give you this one, what is it? It's a D. Where do the D's begin? 3. Is there anything built on it? So what is it? 3D. If I were to give you, nope, I just did that one. Yes. On that particular question, you will have to put whatever axis it's showing on, because they give you that information. I'm not going to expect you to do that. This is not what I wanted. Okay, this is what I was trying to get at though. This is what, so instead of having those little balloon shapes, like I showed you in the homework, theirs is kind of weird because it'll start out showing you a normal orbital, but then it's going to tack things on it, but they're not the same look. So I just want to show you this is, in this particular case, that would be the 3p Z because it's on the Z. Does that make sense? So you can see the 2pz and then stacked on it is the 3pz. So I just wanted to show you in case I can't remember if I'm going to have homework problems that give you exactly that. So this way you'll know what you're looking at. It's a little different than the homework. That's the optional, only because the way they draw it. Okay. So let's get back to where I was. Any questions about recognizing orbitals and nodes? A lot of students struggle with that, so I'm hoping by showing you what I did that it makes a lot more sense. Yes. You could, and it almost looks like Saturn's rings once they add multiples. You'll see two, it'll grow out. So in other words, they'll have the dumbbells stacked on top of each other, plus they'll have what looks like Saturn's rings. That was a P. For the three, oh, for that, I didn't show you the one that was what now? It might have been, but I don't know if it was I didn't think I gave you any with where you had to recognize exactly what d orbital it was yet. I tried to remove all those. So, but yes, it should just be what that P looked like. But then you have what looks like multiple rings around it. Other questions about nodes? Again, these are just areas where the electron cannot reside. So while we said we have electrons in the 2s and the 3s and there are still going to be spaces in between all of that where you're not going to have electrons. And that was determined based off of a Schrodinger equation. There are areas where there's just no electrons. Okay. So the last thing we're going to do today is we're going to get into ions, but I'm going to have to let Dr. DeRocher finish up this conversation. So as we progress, we're going to start talking about ionic compounds. Ionic compounds contain ionic bonds, which is an electrostatic, another word being magnetic, attraction between a cation and an anion. So basically, think of a magnet when we start talking about these. The cation is a positively charged ion that results from an atom losing electrons. The anion is a negatively charged ion that results from an atom gaining electrons. Basically, it is when this positive comes in contact with the negative that you get the ionic bond. Now, folks, to help matters, your cations will be metals. All metals. Your anions will be non-metals and metalloids. So in other words, metals are going to lose electrons. Non-metals and metalloids are going to gain electrons in the formation of an ion. Now, as Dr. DeRocher will discuss, the driving force behind the charges is going to be energy. Ionization energy will be the energy associated with formation of the cation, whereas electronegativity will be, the electron affinity will be the driving force behind the formation of an anion. The ionization energy cannot get too high. The electron affinity cannot get too high, or it just won't happen. So that is really, the energy is the driving force. Now with the nonmetals and metalloids, I will say that the number of electrons gained in the formation of an anion equals the number of electrons needed to have the same number as the nearest noble gas. So group 17 gains 1 electron because that's all it needs in order to have the same number as a noble gas. Group 16 gains 2 electrons because that's all it's needed to get to a noble gas. Group 15 gains 3 electrons because that's how far away it is from a noble gas. They will always gain the same number of electrons because that's how far away they are from a noble gas. And again, we're talking about the nonmetals and metalloids only. We're not talking about the metals that are in those groups. We're not talking about bismuth or tin or lead. We're just talking about the nonmetals and metalloids. Now, as far as the cations, the number of electrons lost is relative to the stability gained. I say it's relative because group 1 always loses 1. Group 2 loses 2. But once you get past group 1 and group 2 and get into those transition metals, many of the transition metals are going to have multiple possibilities, and that multiple possibility comes from the electrons needed to gain some stability. The metals in the P have multiple possibilities because it depends upon what it needs to gain stability. With that, I will let Dr. DeRocher go over the electron configuration of cations and anions. I just introduced the topic, and then he will pick up with why it happens. I forgot sign-in sheet, so I'm doing good to be here. Thank you.